So the last of today's seminar is series is Professor how do you say Francesco, right? Francesco. Francesco Topputo, and he is now doing a very interesting mission to the moon, which is LUMIO, and then there are two missions, CubeSat mission chosen by ESA. Am I right? Yeah.
Yes.
And this is one of them, and we are very particularly interested in this because so far in Taiwan we are also thinking about a mission to the moon. A polar orbiter mission. We don't know what happened eventually, but then we have been have a proposal, experimental proposal just to observe this impact impact flashes. So it's a very popular topic.
Very interesting impact. Yes.
And okay, Professor Topputo, here is your time, please.
Good morning for those who are in Central Europe. Good afternoon for those who are in Asia. My name is Francesco Topputo, and thanks for the introduction, and thanks for the invitation to share the research that we are doing in the framework of the LUMIO mission with you. I'm an associate professor here at Politecnico di Milano in northern Italy, and as the title of my talk says, I will talk about LUMIO mission. So I'm sharing my slides, and now I'm going in full screen mode. Please tell me if you can see my full screen, because sometimes Keynote doesn't work well in full screen mode. Can you see if I change the slide, please?
Yes.
Okay, great. So again, this talk will be about LUMIO. We will see what the acronym stands for, which is a CubeSat mission at L2. It's still a mission study. We will see later on where we are with the mission design, in which phase we are. And before starting, of course, I would like to say that LUMIO is being studied by a consortium led by Politecnico di Milano, which includes Leonardo, an Italian company that is developing the payload, ISIS as CubeSat integrator, supported by TU Delft in the Netherlands, and S&T Norway, which is taking care of the onboard payload data processing. The mission study has been funded so far by the European Space Agency, with the support by the Italian Space Agency, the National Space Office, the Netherlands Space Office, and the Norway Space Agency. What is LUMIO? LUMIO stands for Lunar Meteoroid Impacts Observer. It's a mission proposal. It's a CubeSat mission to a halo orbit at Earth Moon L2. L2 is the Lagrange point beyond the Moon. It's the second Lagrange point. Once at Earth Moon L2, LUMIO shall observe, quantify, and characterize the meteoroid impacts on the lunar far side by detecting the flashes that arise whenever a meteoroid impacts the lunar far side. So we will see how this is now taught to be implemented on the CubeSat. I just wanted to say that back in 2018, we took part to a pretty large competition, which was called LUCE, Lunar CubeSat for Exploration. It was a competition issued by the European Space Agency. We were shortlisted among, we were one of the 4 mission concepts shortlisted by ESA. We were contracted for a phase 0 study, and eventually we won the competition together with another mission called VMMO, still involving a lunar CubeSat for other kind of investigation. As part of this award, the mission was independently assessed later on by ESA at the concurrent design facility at ESA and by their experts. Later on, we were contracted the phase A, and nowadays we are just over the phase A and we are preparing for phase B design. The concept of operation is like the one that you can see in this slide. So the assumption is that there is a mothership. There is a mothership that carries the CubeSats on board and releases them in a orbit around the moon, like the blue orbit that you can see here. From this orbit on, LUMIO will carry out a standalone transfer from the moon environment all the way to the halo orbit around L2, which is the point that you can see on the on the right-hand side here of this cartoon. And once in halo orbit around L2, we are planning for 1 year of nominal operation there. It will permanently observe the lunar far side. At the end of the mission, LUMIO will be disposed in a safe graveyard orbit that will not interfere with the low Earth orbit environment. So this is the mission overview, and these are the assumptions under which the study has been conducted. These were the assumption of the phase 0. During the phase A, we also kind of relaxed the assumption of being already injected into a low lunar orbit, but we also included the possibility to be injected toward a lunar flyby orbit. For instance, the typical injection of Artemis profile, just to have another option as a backup for launch. It's a quite an interesting mission because the science question is to characterize the meteoroids impacting the lunar surface, and the objective is to advance our current understanding of the meteoroid population in the solar system. For what concerns exploration and technology is also interesting because there have been no lunar CubeSats so far. We'd like to initiate what we call a lunar situational awareness, since we are going to deploy human and robotic assets on the lunar surface. We want to quantify the hazard to which we are exposing this asset, and we will see that it's quite interesting. And also we want to test orbit control with CubeSat. CubeSats are always launched in lower Earth orbit. They never perform orbital maneuver. It's in order to extend to use CubeSat in the farther space, we have to accomplish orbital maneuver to adjust the proper mission orbit. For what concerns technological advancement, there are a number of them. Worth to mention here is the development of a high-performance miniaturized optical instrument, onboard payload data processing, autonomous optical navigation, and onboard micropropulsion, and so on and so forth. So it's quite a win-win situation in which we can push the technological development. We can achieve also some pretty nice science return from the mission. This video shows how the mission will look like. So we are injected into low lunar orbit. You will see the CubeSat being injected now. And yes, from injection on, it will transfer to L2L orbit, which is on scale. And as you can see from this particular orbit, we can always see both the Earth and the Moon. Once there, you can see some flashes occurring on the lunar surface in this animation. We have a payload on board, through which we'd like to identify and detect these flashes to later correlate with the energy of the impactor. So that said, yes, let's see why we'd like to do this. We have near-Earth objects which are primitive objects in the solar systems. They have not been processed, so they embed crucial information from the first moment of the solar system, and accessible NEOs are available opportunity to study in order to understand how our solar system evolved. Meteoroids are part of the NEO because they are they have been performed by processing of the NEOs itself, and therefore they are valuable resources to study their parent objects, so asteroids and comets. What happens when a swarm of meteoroids impact a planet or a moon? We have the so-called meteoroid showers, those that are quite easily predicted nowadays, and to which we have been used, for instance, during the summer or in December, when we have the most important meteoroid shower. It happens that the impacts between the meteoroids and either the Earth or the Moon are quite fast, which means that the impact velocity is pretty high. It tends to approach 70 kilometers per second, which is almost the maximum theoretical limit, which is related to the escape velocity from the solar system. So quite high energetic impacts, as we will see in a second. This is important to remember. We'd like to study meteoroid impacts because we'd like to construct meteoroid models in order to be able to predict impacts, quantify the hazard, and understand the temporal distribution of these objects that cannot be observed from ground. As I said, we want to increase the confidence, and we want to increase our characterization of the meteoroid population. As a byproduct of this observation, we can contribute to other fields. For instance, we can contribute to lunar seismology, hypervelocity impact physics, also to study lunar top layer, and ultimately even the space weather. As you can see in this picture, this little flash here is the one that we want to see. This is a real image taken by NASA that has a ground-based program. As we will see, it's run at the NASA Marshall since more than 10 years now. Ultimately, as I said, we want to initiate a lunar situational awareness program for future exploration missions. So the meteoroid impacts, as I said, are unique chances to observe the meteoroids, because you can leverage on their very high velocity, as I said, where the theoretical limit is slightly above 70 kilometers per second, and the currently observed impact speed are, as I said, approaching this limit. There are a couple of effects that we have to consider, which are called gravitational focusing and gravitational acceleration. They are related to the gravitational pulling of the attractor, and to the gravitational attraction, and to the fact that the gravitational pulling tends to bend the trajectory of a meteoroid, and also it accelerates it. So these two effects are important to take into account when studying these effects. We can have that, we can see that the showers, so those that are predictable, they actually approach this limit. However, there are also other kind of impacts, which are called sporadic impacts. The sporadic impacts occur at quite lower velocities, for instance, in the order of 20 km per second or 17 km per second, and these are not predictable as the showers, because in the showers we have the filament of meteor that evolves in a quite predictable orbit around the sun, quite eccentric. That's why we have those high velocities. The lunar meteoroid impacts, the flux that is nowadays observed is between 1,300 and 4,000 impacts per year for greater than 1 kilogram meteoroid. Now, consider that 1 kilogram of meteoroid, one rock of 1 kilogram mass traveling, impacting the moon at 70 kilometers per second, deploys a kinetic energy of 10 to the minus 3 kiloton of TNT. That's the unit of measure that the community that studies this impact uses. The energy of the impact is measured in terms of kiloton of TNT. So 10 to the minus 3 kiloton of TNT, which means 1 ton of TNT. So it's a pretty big bomb on ground. And this is deployed by 1 kilogram of rock because the moon doesn't have any protective blanket like our atmosphere that protects us by this kind of hazard, by dissipating the kinetic energy by burning the meteoroid itself. There are some features in the observed meteoroid. For instance, there is a asymmetry between the near side and the far side that has been postulated. There is also some observation that says that the equatorial flux is greater than the flux at the poles of the moon. And also, as you can see in this image, the flux at the leading side is slightly greater than the flux at the trailing side. The leading side here is the one on the left. The moon moves from right to left. And it might be caused by observation bias. So at the end of the day, we can say that full disk observations are necessary. Full disk observation means that we are observing the whole lunar disk and not only portion of it, like the white squares here that indicate the field of view of the instrument that we use on ground. This is how the meteoroid, this animation on the left shows how the meteoroid evolved in the solar system. And with this observation, we can understand why this, oops, I'm sorry, why this, I'm sorry, I have to go back. Oops, I lost the mouse for a second. Okay, it shows why these showers are quite easily predictable, because this tells us, as I said, how the filament of meteoroid evolves in the solar system. And these orbits are, let's say, recall the orbit of the parent object that was responsible for the formation of this tree. Here on the GIF on the right-hand side that I took from the ESA-funded program called Neliota that is currently run in Greece. It's a GIF that shows how a typical meteor flash appears. And as you say, as you can see, there is a flash appearing here on the top part of the GIF. So what happens whenever a meteoroid impacts the lunar surface? We have that all of this kinetic energy is partitioned into a number of different forms. For instance, the largest part of the energy goes in the excavation of a crater and in the production of a seismic wave in the moon. There are also some particles that are ejected back. So part of the impacting kinetic energy is given back in the form of, again, kinetic energy to the particles. A tiny fraction of this, approximately 1 part on 10,000, goes in the emission of a radiation in the visible spectrum, because the impact site is heat so much that there is a production of a quick flash in the visible spectrum. And the fraction of this energy that goes in the production of a radiation wave out of the impacting kinetic energy is called luminous efficiency, and is indicated by this symbol eta. So nowadays there are programs on ground like the NASA Marshall, like Neliota. There is another program called MIDAS in Spain. These are ground-based programs that are aimed at observing this phenomenon, and the idea is to observe the moon during the lunar night side, of course, and it's also straightforward that these observations are also done during the Earth night, of course, and the rationale is to detect local spikes in the luminous energy of the frame. From ground, we are able to observe magnitude ranging from +10 to +5, and the duration is of this flash is quite lower than 100 milliseconds. So the idea is to observe the moon at a high frame rate and post-process then the pretty huge amount of frames in order to detect these spikes, like in this GIF. There are, let's say, a number of limitations. There are a number of limitations from attached to this concept, because from ground you can observe only, by definition, only the near side. The observations are possible only when the lunar illumination is ranging from 10 to 50%. Otherwise, you will have a large portion of the moon illuminated, and of course, the signal-to-noise ratio will be pretty low. It's affected by noise because there is the earth shine, so there is part of the sun of the sunlight that hits the earth that is reflected back on the moon. For instance, in this GIF, it's the same as the previous slide. In this GIF here, on the bottom right part of the slide, the moon that you can see here, it's not illuminated, but actually is illuminated, not directly illuminated by the sun, but it's actually illuminated by the reflection of the sunlight on the earth. That's why it's visible. There are also a number of other limitations. For instance, the weather that constrains, and the signal that is attenuated by the atmosphere. Now, this sketch here shows us how the geometry of the observation looks like. We have telescopes on ground here, and we have the night side of the Earth. The night side of the Earth. This of course. These observations, as I said, have to be done during the Earth night, and this is the portion of the moon that is illuminated. the green dashed line on the lunar orbit are the portion of the lunar orbit that in which we can conduct this observation. Here, when we have full moon, of course, we cannot conduct this observation. When we have the new moon, this happens during the day on the Earth, so we cannot perform this observation. And the meaning of the dashed line here, the meaning of the dashed green, is because the Earth is rotating, so we have only few hours per night of useful observation time. The story is pretty much different if we go, for instance, in the deep space, or I'm sorry, if we go in the translunar environment, like in this semi circle here, blue. If we are on this semicircle, we can have uninterrupted observation because we are not rotating with the Earth. We can locate also, we can detect also other sources that cannot be visible from ground because of the constraining geometry. We can complement ground-based observation in space and in time. In time, because we can perform this investigation in the other complementary portion of the lunar orbit, and in space because we observe two different globes of the lunar surface. And moreover, we do not have any earth shine, we do not have any atmosphere in between, so which means that we can have quite higher quality products. So that's the idea, the fundamental idea behind LUMIO. And LUMIO will perform this kind of observation when the moon illumination ranges between 50%, 0% when on ground we have the full moon, and 50% again, which means approximately 14 days of steady, uninterrupted observation. As I said, by measuring the luminous energy and by estimating the luminous as I said, the luminous efficiency, we can solve for the kinetic energy. And assuming an impact velocity that sometimes is known in the case of the showers, we can also solve for the mass of the impactor, which is pretty important. As I said, typical values of the luminous energy, of the luminous efficiency range approximately around 10 to the minus 4. Also, understanding luminous efficiency is quite key in this kind of observation. Now, in this chart taken by the paper of Suggs et al. Published on Icarus in 2014, we can see that on the x-axis we have the energy of the impactor, whereas on the y-axis we have the cumulative number of colliding objects with the Earth. So even if this chart contains impacts at the moon, they are scaled back to account for impacts at the moon, at the Earth. In the bottom right part of this slide, we have of this chart, we have high energetic impacts of NEOs, which occur very seldom. For instance, one every 100 years, like the Chelyabinsk impact. And these dots here, these marks here, from the bottom right part all the way up, are associated to observations done on ground. Now you can see that there is a limit here because there is a limit of the size of the object that can be discovered from ground, and there is an empty segment here in between. On the top left part of this slide, you can see this chart. You can see the data that come from the observation of lunar meteoroid impact flashes. The red line are fireballs in our atmosphere, but the other marks, the green squares here, are the lunar meteoroid impact flash observations from ground. Now, the focus of LUMIO is the energy ranging between 10 to the minus 6 to 10 to the minus 1, but we can see that there are uncertainty data here from 10 to the minus 6 to 10 to the minus 4, and there are no data in this central part from 10 to the minus 4 to 10 to the minus 1. So this is what we want to do with LUMIO. I'm sorry. With LUMIO, we want to refine the data here at low energy regimes, but also we'd like to discover new data in this empty region, because there is no reason for having this empty hole in this chart. We have done some modeling of the meteoroid impacts in order to be able to predict the outcome of the mission. So we have modeled all the showers that you can see here in this chart, corresponding to the dashed vertical line. You have the showers as a function of the solar longitude, which is ultimately a function of the date of the year. Solar longitude equal to 0 means 21st of March. And on the left-hand side, you can see the number of impacts with the moon, depending on the shower. On the right-hand side, on the right y-axis, you can see the cumulative number of impacts that has been modeled through our model, in which we have the meteor shower and the sporadic background. The model we developed is called MEGAN, which stands for meteoroid gain. Attached to this model, we had also the performances of the payload, the observation of the lunar far side, and so on. That's why we were able to quantify the outcome of the mission by also considering the observation geometry, because if you see the sketch, the outline on the right hand side here, and you can see this angle beta, okay, the beta angle or the phase angle, we can perform observation only when beta ranges from 90 degrees to 180, because that's why that is the geometry when we have equal or less than 50% lunar illumination. So if we consider this, the beta angle is on the right y-axis here, we can perform observations only when this angle, as I said, is greater than 90 degrees. So only in the white strips there, in the gray portion, we can not have any detection because the moon illumination is greater than 50%. So by intersecting the physics of the underlying phenomenon, so the meteor shower, the orbital characteristic of LUMIO and the payload, we were able to, as I said, to estimate the number of detected impacts that ranges in the order of tens of thousands, let's say from 1,000 to 10,000. And thanks to this estimation, we were able also to see how we can complement the chart that we have seen a few minutes ago. In this chart, we have the simulated outcome of the lunar mission, of the LUMIO mission, in which we have this new data set given by the red diamonds here, which are the impacts that we are able to resolve, that we are able to measure the luminous energy, whereas whereas for the yellow diamonds here, we predict that they are such high energetic that they will saturate our detector, and in those cases we are only able to detect the occurrence of an impact and to have a lower bound for the energy, but we cannot solve for the energy, okay? And they are, let's say, still assumed to have a certain energetic distribution, and they will complement this. So we can see that we can quite contribute to this. Field by providing a number of valuable data because of the time frame of the observation. We can generate a lot of data that can be generated from ground in year time of observation. This is an old sketch of how the instrument looked like. This is actually the one we had in phase 0. It's a simple camera working in the visible spectrum. There is a baffle that is not depicted in this slide. It's a 6-degree field of view camera with 127mm focal length. In phase 0, we used to have a 2x2 defocusing to discriminate between impact flashes and other sources of noise, for instance, in the detector, for instance, the occurrence of galactic cosmic rays. Now, in the phase A, we have 2 detectors. So we have a beam splitter here. We have a dichroic splitting the radiation into 2 different wavelengths. And we have 2 detectors. And only when we have the flash observed on the 2 detectors, the flash is validated and then is stored. In fact, the principle of operation of the camera is to observe, is to take 15 frames per second and to process on board these frames in order to store only those that are interesting from the scientific point of view and to throw away all the other. Very quick overview of the orbit. The orbit is a peculiar orbit. It's called, as I said, halo orbit around L2 that assures a full disk coverage of the moon. Permanent far side observation, quite easily accessible from lunar orbit, is free of eclipse. This is very important from the technological point of view. And it's in near 2-to-1 resonance, which means that the period of the orbit is about half of the period of the lunar orbit around the Earth. This is the concept of operation, meaning that in the blue portion, we will conduct science. In the orange portion of the orbit, we will conduct what we call the engineering and navigation phase. This means that we will use the payload to perform an experiment of autonomous navigation by processing the image taken by the same payload that we use for the scientific purpose in order to solve for the position of the spacecraft itself. This is because the CubeSat need to be autonomous in order to be cheap in terms of ground operation. This is how the CubeSat looked like at the end of phase 0. The total mass was slightly higher than 20 kilogram. You can see the gray stuff here is the payload. We have star trackers, solar arrays, and so on and so forth. This is the current status of the mission. As I said, this was started at the end of 2016 by the issuing of a challenge by ESA. We conducted the phase 0 in 2017, the CDF study in 2018. For some reason, in 2019, nothing happened. But in 2020, we conducted the phase A, which was over at the end of March this year. And now we are getting prepared for the next mission phases. Luckily, our national delegation, so Italian Space Agency and others, are talking to ESA. They are all willing to support the mission. So hopefully, by the end of this year, we will start the phase B. In conclusion, this was an overview of LUMIO that was awarded the winner of ESA Luce Sisnova competition. The phase A, it's written ongoing because this is a an old slide, but it's over. As a number of peculiarity, unique opportunity for science and exploration, and unique opportunity also for technology advancement of Lunar CubeSat. The acknowledge, of course, go to the European Space Agency for supporting this, and also to Italian, Dutch, and Norway space agencies or offices for supporting the phase A of the mission. I think I was quite on time because if everybody agrees, I would like to take a few questions, if any, in order to use the remaining time allocated.
Yes, certainly. Thank you so much, Francesco. This is a very interesting, and comprehensive presentation on the LUMIO mission. And anyone has questions, please unmute yourself and ask the questions to Professor Topputo. If no one has question yet, I would like to ask you a couple of things first. You said you will have two detectors. Do they have a different filters?
The optic is the same.
Yes. Yeah.
There is a dichroic in between that splits the radiation. The detectors are exactly the same.
Yes.
Okay. So the only element that is additional with respect to the layout that I presented is the presence of a dichroic that splits the radiation, if I'm not mistaken, around 800 nanometers. Whatever is lower than this goes to one detector. Whatever is higher than this goes to the other detector.
Very good.
And that's it. But the detectors, in order also to make the design simple, the two detectors are the same, exactly the same each other.
Because we are also planning a pair of telescope, 50 centimeter on the ground. One of the purposes is really to monitor the lunar impact flashes. And we use two filters. The idea is that, of course, as you said, is to check the false positives. And also to using those two filters, you might be able to even to estimate the temperature of the flashes.
Yes, and yes, this is exactly also the reason behind having this split of the radiation, because you have two data points in the black body law, and then you can retrace the black body law in order to have to solve for the temperature of the flash. So somehow we'd like to do something similar to this. And so if I understood correctly, you have two filters, so you have two different optics and two different cameras, right?
Of course, in principle, we hope that the telescope are the same. They could have a somewhat different. So we need a lot of calibration to do that. But in principle, they should be just as close to each other as possible. Of course, you are now talking about optical wavelengths. So have you thought about doing using ultraviolet or infrared?
Yes, we did. We did think of this, but we had a driver that everything had to be cheap, because the philosophy of the CubeSat is that they have to be cheap. So if you go in this spectrum, the design of the instrument becomes a little bit more tricky than in the visible spectrum, and the cost of the lenses increase, and and also the design is more complex. So also the phenomenon occurs in the visible spectrum. So let's say the safe choice was to stay in the visible spectrum in order to not to increase the cost of the instrument itself.
At the end, you said you thank, of course, the Italian agency, space agency, and then in the Netherlands. Is that Netherlands?
It's Italy, Netherlands, and Norway.
Norway, and
yes.
Does ESA pay anything, or ESA doesn't pay anything?
Well, ESA funded the phase 0. And they managed all of the phase A. So the project is an ESA project, but it's backed by the national space agencies that I mentioned, because it's framed into a program called GSTP, which is a program that is subscribed by the national space offices on a voluntary basis. So that's why it's like this.
I must say this. Italian space agency has been doing very well, and they seem to have a lot of money.
Hopefully they will find some to fund LUMIO.
Okay, very good. Yeah, and the mission will start from your timetable is starting in 2024.
Yes, the idea is to have a launch in 2024. I have to admit that it's quite tight now. It's quite tight schedule, but with the CubeSat, never say never, because the philosophy is that they have to have a quite short development time. So if you take 10 years to develop a CubeSat, it means you are not doing a CubeSat anymore. So we'd like to think that 2024 is something that can be done. Although I have to say that it's quite optimistic.
There's a Japanese CubeSat mission also doing lunar impact flashes. You know that, right?
Yeah, it's called the Culius. Yes, I know it. Yes.
And would that be done in the same time scale?
I don't think so, because they are supposed to be launched with the Artemis 1 mission, which, if I understood correctly, will happen before the end of this year. So they will, yeah.
Anyone want to add some information to this? Nishino-san, do you want to add something?
No. I don't have anything to add.
Unfortunately, Shinsuke Abe-san, he's not online because Abe-san, Professor Abe, he is the PI of this Japanese lunar impact flashes experiment.
Oh, very good.
And he told me that he might be joining a very rich Japanese billionaire to go on a spacecraft around the moon. So he might be the first person who would be watching the lunar impact flashes with his own eyes.
Oh, very good. Very good. Cross fingers for him. Maybe I will be the second.
So no one can beat this. Yeah. Any other questions from the participants here? I think I got the information I want about the filters and the. So you also make I think I must say that you have make a very detailed assessment on the impact frequency and all that. And very
yes,
nice.
We have. If you want, we have this model. We have developed this model with one model is called Meteoroid generator. It's a model of the meteoroids in the solar system and so on. And the other one, it's called payload orbit environment. It's called POE, in which we plug on top of the physical phenomenon, we plug the optical and the characteristic of the detector for the instrument, and also the characteristic of how the object moves in space. Now, if you want, if you have your instrument on ground, we can make some analysis in order to predict the outcome of your observations.
That would be very nice. Yeah, they were very helpful. Yeah, yeah.
So we can get in touch offline for this, and we are pretty open to collaborations. So.
Yeah, thank you. Because before, about a month ago, Krista Avellino, she gave a talk also on the ground-based measurements. Yeah.
Yes, yes. She is aware of LUMIO, and she was among the people to which we collaborated in the very early phases of the concept of the mission.
Yeah, she's now making a big project, over there to do the same thing. All right,
Yes.
Professor Topputo, thank you so much. That this is a very interesting presentation. And
it's been a pleasure. It's been a pleasure for me, and I wanted again to thank you for the invitation and to invite you to not hesitate to get in touch with me in case you have follow-ups. And again, have a nice evening.
Yeah.
For us, it's still morning. You are almost done with the Monday. We are still
right
to do.
And you have a full day to work.
Exactly.
Good day. Yeah. Thank you so much.
Thank you very much.
Yeah.
Bye, everybody. Bye-bye.
Bye-bye.